All right, folks, we're back to section 3.12 of PRML, talking about the geometry of least squares. Now, it's been a while since I posted a video, and the reason why is because I wanted to kind of give a little bit more insight and give a bit more details on what's going on in this section, because the section is very short, but I think this idea of least squares, optimization is a very important and useful one for all sorts of reasons, geometric reasons and analytical reasons, and for giving us a good playground to try out our analytical tools of linear algebra mainly and calculus. So what I thought was I would actually write out kind of my own supplement to these notes, and that took a bit longer than I expected. But they're mostly finished now. So what we're going to do in this video is we're going to go through this section. We're going to go through this section, and it's very short. And then what we'll do is we'll switch to my notes, and I'm going to give you the link to my notes. They're on my blog, but I'll also give you the PDF. So then we'll go through that together and try to get kind of a bit of a more in-depth understanding of what's going on here. And so after this session, it would be actually very useful for me if you guys could comment to say whether you found those additional notes useful, whether it was kind of worth that exercise, or whether you would have preferred it we just kind of kept going. So let's just see. I thought it would be fun to organize my thoughts. I actually originally tried to just talk about those ideas as I went, and I found that I was actually there was too much I wanted to say, and it was getting a bit jumbled. So I thought it's better to just write it all out, and then we can kind of go through it in sequence together, which is what we'll do today. Okay, good. So let's just go through this first section now, and then we will switch to the notes. Okay, so remember kind of the setting we're in. So let me see if it's worth scrolling up. Yeah, so we've got so we've got kind of a model like this where you've got n data points and targets, and you're going to fit some linear model to them, and you're going to assume the targets are your model plus some noise. Okay, so let's go to our section and see what we're doing. Okay, so at this point it's instructive to consider the geometrical interpretation of the least square solution. So to do this, we consider an n-dimensional space whose axes are given by the Tn. So that this boldface T, this vector T, is an n-dimensional vector in this space. So now we've put all of our data points, all of our targets that were kind of scalars, single values, into this one single vector in its n-dimensional space. And in this picture up here, it's just a single point. So that's kind of like one set of targets. Each basis function phi of j of x of n, evaluated at the n data points, can also be represented as a vector in the same space denoted by this kind of curly phi, as illustrated in figure 3.2. So this, for example, would be your feature number 1 evaluated on all data points, feature number 2 evaluated on all data points. Note that phi of j corresponds to the jth column of our design matrix phi, where phi x of n corresponds to the nth row of phi. If the number m of basis functions is smaller than the number n of data points, then the m vectors will span a linear subspace S of dimensionality m. So what he's saying is you're going to have your features evaluated on all of your data points. That'll give you one vector. If you do another feature, that'll give you another vector. And these will then, the set of all linear combinations of those will give you a span. We'll give you that linear span, this set here, S, which kind of extends all the way out. And his point is that if you have fewer features in the dimensionality of the space, which is the n in this case, then you're not going to be able to cover the whole space. But what you will get is this kind of slab that's sitting, this linear subspace that's kind of slicing up a portion of the space. So you typically won't be able to hit T exactly. You're going to try to find a point that's kind of closest to it. Okay, then the m vectors will span a linear subspace S of dimensionality m. And we define y, boldface y, to be an n-dimensional vector whose nth element is given by our model evaluated at our data point, where n is 1 to n. Because y is an arbitrary linear combination of the vectors phi j, it can live anywhere in the m-dimensional subspace. So this whole place is our oyster. We can be anywhere we want in there. But the question is, where should our estimates show up given this particular data set? The sum of squared there is then equal up to a factor of 1/2 to the squared Euclidean distance between y and t. Thus, the least square solution corresponds to the choice of boldface y that lies in the subspace that is closest to t, and that's going to be, you drop this kind of 90-degree line. Basically, you just drop a line to the surface, and where it hits the surface, that's your estimate, assuming gravity is coming from the surface, of course. Okay. What else do we have? Yep. Intuitively, we anticipate the solution corresponds to the orthogonal projection, perpendicular projection of T onto the subspace S. This is indeed the case, as can easily be verified by noting that the solution for Y is given by phi, the design matrix of WML, and then confirming this takes the form of an orthogonal projection. So we'll see how to do this in the notes. In practice, a direct solution, then he talks about some of these numerical difficulties, but he does highlight singular value decomposition, which we're going to use in the notes. So great. So I think that was kind of you see it was kind of a very short section on this geometric picture. So that's why I thought we would all benefit from going to the notes and taking a bit more time with the situation. So we're going to be starting with this and then kind of talking about the problem in kind of a more expansive way. So let's do that. Meantime, let me just move this over here. Great. Okay, so here are the notes. This is for my blog, and I'll post it. I'll give you the link, of course, and I'll also post this PDF so you can use it if you find it useful. Okay, so yeah, here we go. Okay, so what do we do? So the maximum likelihood estimation requires minimizing this function, right? That was the function we started with in the section. So it's 1/2 of the difference between the data points and their projections onto our features. Here the vector area contains each of our features evaluated on the single input data point. So what I'm saying here is just notation basically. So 5x of n is each one of our features going to be evaluated on a single data point. It's going to be this n-dimensional vector. Oops, sorry, actually this is not n-dimensional. This should be m-1 because we have m-. So this is actually it's an m-dimensional vector. Okay, so we're interested in getting a deeper understanding of this minimization. Okay, so the very first thing he said is, the way the error function that we've kind of written it up here is expressed about emphasizes the contribution. Let me switch. It emphasizes the contribution of each data point, right? Because we're just summing over each of the data points up there, right? So of course, his very first move was, why don't we pack all the data points into one giant vector and look at things that way? So another way to interpret that equation involves in changing our perspective from single data points to viewing the data set as a whole. So that's kind of what I'm trying to say. We do this by first packing all of the target values into a single n-dimensional vector T, which is that. And from this perspective, our entire set of n target values is a single point in n-dimensional space. So that's just this point right here, which we've already discussed. So you guys are all familiar with that. And similarly, we pack our predictions for each observation into a single n-dimensional vector y, and this is y. So for every single observation 1 to n, we're going to have some prediction. And that prediction is going to be formed by taking these weights, doing a linear combination of our features evaluated on that data point, weighted by our weights. And that's kind of how we write that. Okay, and so now we're going to see that actually the error function is simply twice the squared length of the difference between the target vector, that's t, and our predictions. And so the way we're going to see that is, we just simply plug it in, right? So we've got twice of this error function. Remember, it's got a 1/2 in front of it. So twice this error function is the sum on these n elements of t of n minus this thing evaluated on xn. Well, t of n just states that it's as it does, but this weight projection that's actually the nth element of our projection, right? When I've written this exactly. So now we've got this sum happening over n elements of a difference between coordinates. And what's that? Well, that's just the length of the vector whose elements are those differences. And you can just write it this way, or you can just see that this is actually just the difference between one vector and the other. So minimizing the error function is the same as minimizing the distance between these two vectors. So that's kind of the big geometric idea of what's kind of going on geometrically. Okay, so now then he said, okay, well, we want to minimize this thing. T is fixed. Y is the thing we can control, but how much can we control it? Like, can we actually hit T exactly? What is the range of values that we can get? So let's look at so that's what we're going to do now. So we have to consider the range of values that our predictions Y can take, since any solution we find must live in that range, right? We can't, we just have to see what values of Y we can get. To do that, we're going to expand y. So here's y. We just expanded out into its coordinates, and each one of them we said was a linear projection of the feature evaluated on that data point, and we just kind of flip it around because these are just numbers, right? So we can kind of transpose them. So it's now phi of x of 1 to phi of xd transpose, and then we take the w out, so w is sitting there, and then we arrive at this equation that says that our estimate is a linear combination, according to w, of the columns of this matrix here. And so what are those columns actually? Well, we're just going to write it out explicitly, right? So phi is this thing. Okay, so that's that. So now let's just physically write it out. And so we get, okay, well, it's the first feature valued on the first data point, then all the way to the m minus 1 feature on the first data point, and then so on. So we can see that the columns are actually single features evaluated on all n data points. So notice that essentially what we have is we've got kind of everything's kind of living in n-dimensional space from one perspective. We've got our targets, which are living in n-dimensional space, one for each data point. We had our predictions, one for each data point, so again a single point in an n-dimensional space. And now we've got features, and each of these are also a single point in n-dimensional space. And so the game where we're going to play is, can we combine these n-dimensional points, these n-dimensional vectors, into this vector y, and try to get as close as we can to t. So these are kind of our tools, basically, our little our basis that we can use to try to capture y. So phi, you can also see it as being a bunch of columns of individual features evaluated in all the data points. Notice that I've dropped the n subscript because each of these features is going to be evaluated on all of the data points. Whereas when we look at the rows are all the features evaluated on a single data point. So that's why we've got the index as well. And that's basically what I'm saying here. So notice we've got the two perspectives. We can either view phi as a stack of n rows, where each row is every feature evaluated on one data point. So it shouldn't be not on A1, it should just be on 1. Or as a stack of m columns, where each column phi, I guess it wouldn't be a stack, whatever, collection maybe. Collection of m columns, where each column phi j is one feature evaluated on every data point. So that is what we're talking about here. So there's two perspectives, and it's always really cool to keep those in mind. It's the same matrix, but you can view it from two perspectives. And now the one we're going to use mostly is going to be the latter view, which is particularly insightful because it allows us to express our predictions y for the entire data set as a linear combination of the different features evaluated on the entire data set. So that's kind of what I was saying before. So when we got this equation y is phi times w, well, what does that mean? Well, it means that we are taking these features, evaluated on the entire data set, and we're weighting them by w. And so we need to find a good weighting. So now returning to our minimization problem, we can see now that since we are free to set the weights w to any value we like, the range of predictions y available to us when performing the minimization are any linear combination of the features phi j. So the set of all such points from the plane through the origin called the span. So this is the important idea. The span is a very important idea to have in mind. It's a very useful idea to just be aware of and to think with. You've got a bunch of vectors. What is the set of all linear combinations of them? Well, it's the span. And so the figure above shows the span for two features, phi 1 and phi 2. So let's go have a look at that. This is exactly, so there's phi 1, phi 1, phi 2, and this is kind of and it kind of continues on all the way, set of all linear combinations. And here it looks like they're kind of orthogonal, they're kind of perpendicular to each other. They of course don't have to be. They can be like this, and again, they'll cover the same space unless they're exactly on top of each other. But if they're not, then no matter how close they are, they'll still cover that entire space. Okay. So the span, a very important topic, very, very much worth learning. Okay. All right, so the geometric approach to our problem is then clear. We want to find the point in the span of the features that is as close as possible to the target vector t. We can also now see that a good set of features is one whose span comes close to the target vector, right? So if, we remember that we can't, in these settings, our features are picked beforehand, so we don't fit them to the data. And so then we can say, well, a good set of features is one where the span tends to be close to our targets, and a bad set is where the span is will just be will produce a linear slab where the points are all kind of very far. It's almost kind of orthogonal to the targets. So that kind of gives us a way of quantifying what we actually mean by good features and bad features. But again, in this setting, those features are fixed. So you have to either know something about the entire set of data, that you're likely to encounter, or you just got to be lucky, I guess. Ideally, the span would contain the target vector, meaning that we could reduce the error to 0. But when we have fewer features and observations, which is the case that we're considering here, this will usually not be the case. It'll be very unlikely that, of all the places that target vector could go, it'll just happen to live in your two-dimensional, m-dimensional subspace. Instead, we'll settle for the point in the span that's closest to the target vector. We'll now find this point in 3 different ways. Now we're going to do this in 3 different ways, so let's get to it. So the very first one is kind of a turning the crank approach. So gradient descent, or setting the gradient to 0, basically. So this is perhaps the simplest approach and does not require any geometric insight. So you don't even need to know what you're doing. We just have this function. Let's just minimize it. We simply compute the gradient of the error function with respect to w, set it to 0, and report the answer. Because our error function is bowl-shaped, and we'll talk about this at the very end, it's just like a parabola, it has only one location where the gradient is 0. So we don't have to worry about multiple solutions, local minima, etc. So the point is that when you find a point where the gradient is 0, that will be the solution, and it will be a local minimum, and it will be a global minimum. So this is the simplest possible case that you'll encounter, so it's very good to master it. The gradient of our error function with respect to Wt is, if you go back to how to take gradients, you'll see this, or you can just work it out by hand. It's the sum over data points of the errors, the residuals, weighting, and they'll be weighting the corresponding feature values of that data point. So I just prefer to work with columns, W's rather than Wt. So let's transpose this, and so again it's essentially the same expression, but now we've just got 5xn instead of 5xn transpose, and it's the gradient with respect to w. We set this to 0, and then we just rearrange things. So now I put these t's and the phi's, we put them on one side. And then we've got this sum of phi times phi transpose on the other side. So now, what is this actually? What are we actually doing here? So the left-hand side is a linear combination of our transformed inputs. So we can write it compactly as, well, let's see what it's doing. So we're doing a linear combination of phi of xn's. So we can just put those into a bunch of columns. We've got t1s forming the weighting. And now it looks exactly like the transpose of our design matrix. Remember, our design matrix had, remember our phi looked like phi x1 transpose all the way to phi xn transpose. Well, what we've got here is, we've got the phi's they're not rows, they're columns. So it's the transpose of this matrix that's showing up. So this left-hand side just becomes phi transpose times t. As for the right-hand side, so now what is this thing, right? We got a sum of, and this is a very useful trick to know. We've got a sum of, of outer products of columns with rows. So to kind of figure out what that is, we just recall the very useful observation that to multiply two matrices, we can sum up the outer products of one column from the first and a corresponding row from the second. So what I mean by that is, if we've got A, which is a bunch of columns, A1 to AN, and B is a bunch of rows, B1 transpose to B1N, and there should be a transpose here. Then when you multiply them, all you have to do is you just take the sum of the outer products of this one and that one, this one and that one, all the way to this one and that one, which is what we have here. So here we just now turn that around and we say, well, what we have is a sum of those outer products. So the matrix that we have must be one where the columns are phi times one where the rows are phi transpose. Well, the ones where the rows are phi transpose is just phi, this is capital big phi, and the one where the columns are the phi's, well, that's just phi transpose. So what we get is that this, this right-hand side is just phi transpose phi times w. So we've got to put the pieces together, and here is the equation that we get. Okay. Now phi has, in our situation, will have more rows than columns, so phi, so now we want to solve this thing, right? So phi transpose phi will in general be invertible. And why is that useful? Because now we want to get w by itself, right? So then what we can do is we just multiply on the left by phi transpose phi to the minus 1, and we've got our estimate, w hat, where the hat indicates our solution for the weights. And now to get the actual to get the actual predictions, we have to multiply those by phi. And so we do that here, and we get this complicated looking, but actually quite intuitive, and you'll hopefully by the end of these notes you'll understand where it comes from, expression. Now this equation can seem a bit mysterious, and we'll try to clear up some of the mystery a little bit later. But let's just for now just do a little sanity check. We call it the reason we can't minimize the error to 0 is because our target vector t is n-dimensional and our span is only d-dimensional. So the target will live off the span in general. Right? So all we're saying is, if we go back to the picture, I'll just draw it down here again. Yeah, if you just go back to the picture, again, you know, you've got like phi 1, phi 2. Well, this is, and your target is up here. It's going to live in three-dimensional space. You're not going to be able to hit it exactly. So the target will live off the span in general. However, if we had exactly as many observations, so now we're talking about the case where, let's say we lived actually, you know, the whole situation was two-dimensional, so that, you know, the phi's were two-dimensional, you know, we're living in that space, but the target was also in that space. So there's t. Well, then in that situation, we could actually recover it exactly. So let's make sure that our formula does give the right answer in that setting. So if the dimensionality of phi, so phi is a square matrix, so it's, you know, it's m by m or n by n, whatever you want to call it. So the number of examples we have is the same as the number of features. So if we had exactly as many observations as features, then the dimensionality of our targets would equal the span. So the target would be living in m-dimensional space, which would be your whole space, and your phi's would span that space. So you should be able to reduce the error to 0, and your estimate should then become t. The closest point you can get to t is t. So is that what we were getting? Let's check that our equation above gives the same answer. So when we have as many observations as features, phi will be a square matrix, and will usually be invertible, and therefore, usually unless there's some funny business, which actually will mean that the span isn't actually m-dimensional, so it will be, in general, will be invertible. And therefore, phi t phi will be invertible, and so we can now do just do some our simple linear algebra. So this is our expression. We take the inverse of this, which is phi minus 1 times phi minus t, and now we just remove the brackets. This cancels that cancels that, and we get t. So as we hope. So at least in this special case, our formula above, which we don't necessarily understand yet, but at least it gives the right answer. Okay, so that was one kind of turning the crank approach. And now let's try another approach, which is kind of a bit more geometric. So, you know, the first approach was very mechanical and not very geometric, and we had to use calculus. So in our second approach, we'll use geometry to avoid doing calculus. So in particular, we'll use a simple observation that the point in the span closest to the target vector is directly below it. And this is what he also mentioned. So in other words, the vector we're trying to minimize, t minus y, which points from our solution, which lives in the span, to the target vector, will be perpendicular, orthogonal, to the span. So all we have to do is find a y hat such that t minus y hat is orthogonal to the span. So again, so the point here is we've got, let me draw this out. Here is our point t, and the nearest point is going to be an orthogonal drop onto the span S. So this is going to be y hat, and this thing is going to be t minus y hat, and you can see that it's perpendicular to the span. So that's going to be the idea. That's going to be the idea that we're going to use here. Okay, so how do we find such a point, right? Now the span is generated by all linear combinations of our features, phi j, so it suffices to check. So we don't have to check every single point. We can just check the set that generated them, and then if it's 0 with each one of those, well then any linear combination will also produce a 0. So it suffices to check that t minus y hat is orthogonal to each one of these feature vectors. That is, phi j transpose t minus y hat is 0 for all j, for all of our features. So there, you know, so all of our features, when you at the solution, all of our features can't contribute anymore, basically. If we can find such a y hat, then we're guaranteed that t minus y hat is orthogonal to the span, because for any point in the span, if we project it onto that vector, it'll just be a linear combination of zeros. It'll be 0. So all we have to do is just check those those feature vectors that are generating our span. Now we can write our orthogonality condition above as, so this was this phi j, this thing, as phi j transpose t is phi j transpose y hat. And now if we pack that into, into one big matrix equation instead of a bunch of individual equations, we get, phi 1 transpose t all the way to phi m minus 1 transpose t. That's the left-hand side. Has to equal the same thing but times y hat. And so we just pull out the t and the y hats. And what do we have? So on the left-hand side is this, so we can bring it out. Our design matrix had the features as its columns, whereas the matrix above has the features as its rows. And we recognize the transpose that is, so we recognize that this is the transpose of the design matrix. So we can just write our conditions as phi of t times t is equal to phi transpose, times y hat. So it's just kind of, just using these conditions, these orthogonality conditions, we just got a condition, a matrix equation for what should happen at our solution. So now, to get the solution in terms of w hat, that's kind of what we were after. We call that y hat is phi of w hat. So left-hand side, phi transpose t is phi transpose times phi of w hat. And this is exactly the equation that we had before, and it has the same solution. So we managed to get the exact same solution, but without just using some geometric intuition and linear algebra. So we didn't need to use calculus then. And that kind of shows you how to express these ideas of orthogonality, using linear algebra. Okay, so the next bit we're actually going to use SVD, which is a very powerful tool. For kind of decomposing what matrices are doing. So let's get into it. It's going to kind of give us a lot of insight into kind of what's happening, I hope. But it's going to be a little bit more involved. So you have to kind of be a bit more comfortable with your linear algebra. Okay. So we've seen above that the solution we're after is the orthogonal projection of the target vector into the span of the features. Right? So if you had an orthonormal coordinate system for the span, we can compute this projection easily by simply projecting the target vector into each one of these coordinates. So that's kind of like, all I'm saying there is, let's say this is your target vector t, and you want to project it onto x. So if if you knew, so it's really simple, right? Because we know t is equal to, t1 and t2, and so we just project it onto this first coordinate, which is t1. So we don't have to, if we knew, like if we had someone kind of just giving you, okay, well, I'm going to give you the vector for that projection, which is like, let's say the 1, 0. Then all you do is you don't have to go through this this rigmarole of forming a design matrix, all this stuff, right? If we kind of just knew what the direction was, then we could just immediately just project onto that vector. So we could just immediately compute our t hat would be 1, 0 transpose t1 t2, which would equal t1. So we wouldn't have to kind of go through all this stuff. And so that's essentially what I'm trying to say here, is that one way to look at this is that, well, if we kind of already had our coordinate system for the span, then we could just immediately project into that system without having to go through the design matrix and the phi transpose phi and all that stuff. So hopefully you kind of get what I'm trying to get at. So how are we going to get such a coordinate system, right? Like in this case, it just happened to be that the coordinates were along the x-axis, but how do you get them in general? We apply the singular value decomposition to our design matrix, and we'll find it useful to express phi from the two perspectives. So let's repeat that again. So phi is a bunch of columns of the features, or the rows of all the features on the single data points. And SVD is going to give us decompose phi into a product of this matrix U, which is going to give us the basis of features that we're after. Diagonal matrix of singular values, and then again an orthonormal basis for the rows. And the piece of it that we need is going to be this basis for the columns. This orthonormal basis is going to give us for the columns. So orthonormal just means that they're all length 1 and they're all perpendicular to each other. So when you project them onto each other, they give you 0. So essentially just giving you coordinate system for this feature space, for this kind of output space. So if we had this U, then our solution would then be u transpose times t back onto u. So again, going back to our our example projecting onto the x-axis, this would be kind of like saying, well, the solution is 1, 0 times 1, 0 transpose times t, right? So our projection in that case would be 1, 0 t1, which is that projection that we had of t and t1. So it's the same idea, but now doing it for when you have more than one dimension. And let's see why this works. So multiply the matrices like we did above. Remember that the rows and columns thing. So UUT is just a sum of, for all the dimensions that we have, of I is equal to U1 to U1's transpose. So where UI, this should be, is the ith column of U. When we apply UUT to our target vector, we get, well, it's going to equal this sum of UI UT times T, which is a sum of, so it's now going to be a linear combination of the columns of U, so our coordinate axes, weighting each of them by the projection on the corresponding column. So that's all there is to it. So we did SVD. SVD gave us a coordinate system for our features, for our feature space, and we just use that coordinate system. We don't have to go through. We can just throw away phi now. We can just compute the projection using U. So here was the solution that we found with this direct projection method. Now, the solution we found by direct projection matched our previous solutions. Well, let's have a look. So this was the old solution. So let's now use SVD to write out what that actually is. So we apply SVD to each one of these parts. So there's USV transpose there, the transpose of that on the other side, and then when you multiply phi t phi by itself, you'll get V s squared V transpose. And when you invert this middle bit, well, you end up just inverting the diagonal elements. So when you multiply all of that out, you get indeed that this formula, what it was doing was actually exactly what we thought. It's projecting the data point onto the span. But in the phi case, we hadn't applied SVD yet, so we had to kind of use this more complicated formula. But if we already had that basis, if we had an orthonormal basis for our span, we could just use that directly to get the solution. So what we had before looks exactly like is equivalent to just doing that direct projection. So that kind of gives you kind of a third approach to do it. Okay, so now now we've kind of seen SVD a little bit, so we're kind of a little bit used to that. So what is this phi t phi that keeps showing up, and also what is this inverse that's showing up here? Like, what are they actually doing? Now, since phi is this matrix, our design matrix can be seen as a bunch of the of our features evaluated on all our data points. This phi transpose phi is a matrix whose elements are the dot products, kind of the overlaps of our features with each other. So if we look at kind of the ijth element, well, it's going to be the ith feature projected onto the jth feature. And so high values, relatively to the others, indicate that a pair of features are quite similar. So now we care about this because intuitively we compute our estimate by first projecting the targets into the space of our features. So that's kind of the very first step. Now this is also sometimes called the analysis step because we're decomposing or analyzing our input into its projections into our features. So that's kind of what we're doing. Remember, so this is equivalent to taking each one of these features and projecting, finding its overlap with the targets. So we're kind of analyzing, we're kind of decomposing. We then construct our estimate as a linear combination of those features, and this is the synthesis step because we're kind of rebuilding things again. So there's kind of analysis and synthesis. So let's do that. Analyzing, and that analysis step, synthesis. Now, if we simply perform the synthesis by weighting our features by the projections on the input, we would end up double counting features with high overlap. So that's kind of the whole point. Like, that's kind of the idea of why we need phi t phi, and actually it's inverse, right? Because if you have a couple of features that are really overlapping a lot, they're very similar. Well, when you compute the overlap of one, when you compute the projection onto one, and then you compute the projection onto the other one, and you use both of those values to then reconstruct, well, you've kind of double counted one of them basically, right? Because the other one, the second one is basically like the first. So we don't want to be including like twice that direction in our synthesis. We only want to, we want to include some smaller amount. And so the inverse of this matrix that's going to show up in a bit is going to essentially take care of that for us. Okay, so the way we're going to kind of see this in action, we're going to actually start with a design matrix that we can kind of handle and where we can adjust the overlaps and just see what it does. So let's imagine that our design matrix is really simple. So it's the identity. So our phi in this case is just the identity matrix. So our estimate of any input t would be y hat is, phi transpose times t. So unsurprisingly, our estimate matches the input perfectly, right? So in that case, we have as many features as data points, and our design matrix is really simple. And I transpose I minus 1, blah, blah, blah. It just becomes the identity. So, our hat, very, very simple situation. And importantly, our features aren't overlapping, right? So in this setting, our features are looking like this, right? Remember, these are the columns. These are our features, and they don't overlap. They're perfect. They're completely not overlapping. Now let's try the same procedure, but with a design matrix where we can adjust the amount of overlap between the features. So we'll do this by adding epsilon to every element of our design matrix, and we call the result I epsilon. So here's I epsilon. I'm just going to have the identity, but now I'm going to add this epsilon to every element. So now our features look like this, right? And so now these epsilons are common into all the features. That's going to introduce some overlap. So now let's figure out what those overlaps are. Well, we just do the transpose thing, and we end up getting that it has kind of the overlap matrix has the same shape, but there's just some other constant delta that's related to epsilon. So it's kind of the same kind of thing, and delta is just the epsilon plus epsilon squared. So it's kind of increasing function of epsilon as we expect. So it has the same form as our design matrix, just with epsilon replaced by delta. And we can see that delta allows us to adjust the degree of overlap as we desired. Okay, so that just says, look, we've got this kind of toy example to work with, and we can adjust the overlaps. And now let's try to reconstruct things, analysis, synthesis, just like before. None of this minus, phi transpose phi minus stuff, and let's see what happens. So to compute our estimate, we need IE transpose, but this is the same as, because these are symmetric, as IE transpose IE for our design matrix since it's symmetric. So when we apply our simple estimation procedure from above, so analysis and then just synthesis, or just rebuilding back, well, what do we get? Well, this product was just I plus delta, 1t, which is just t, which is what we wanted. So in addition to t, our estimate now includes an extra term that's related to the sum of the elements of t. So now we've got this additional thing hanging out. We just wanted t, but because of this, and remember delta is 0 if the overlaps are 0, and it increases as epsilon increases. So this overlap that we've introduced is now kind of adding this additional term to our estimate. So we're getting farther from the solution. This addition takes us farther from the optimal estimate, and it's clearly contributed by the overlaps because look at it, the delta is basically what's causing it. And reflects the fact that we didn't account for these overlaps when synthesizing our estimate. So that's where phi transpose phi, or in our case, IE transpose IE comes in. We use its inverse to cancel out the effects. To cancel out the effects of the overlaps. So let's first compute so we're going to now do this. So let's compute the inverse. So we'll use this very useful Sherman-Morrison formula if you haven't seen it before. So we'll just to find the inverse of this matrix, and it ends up being, again, of the same form, identity plus 1, 1 transpose. 1, 1 transpose is the matrix that's just all ones. There's a typo here. It's the same form as I epsilon, the identity plus a single value added to every element. That's coming from this. But now this value is negative. So instead of having kind of positive overlaps, instead of having like these kinds of overlaps, the effective overlap here is negative. So it's kind of like the vectors are like that. They're kind of undoing, they're doing kind of the opposite thing of the overlap. They're kind of doing the reverse. So now, this value is negative, so it acts in the opposite direction of the overlaps to cancel them out. When we then sandwich this adjustment between our analysis and synthesis steps, we get the results we were after. So now, instead of just I epsilon transpose, we're going to put this adjustment in. So going back to our old formula, and as expected, you can go through the math and you end up getting t. So our estimate was this optimal thing that we were after. So once we account for the overlap, our estimation procedure returns the target vector as it should. So we have to account for that overlap, and that's what this guy in the middle is actually doing. Now above, we picked a particularly simple design matrix example to help us understand what's going on, but the same basic idea holds in the general case, which we can see using SVD. So to do that, we can go back to our direct projection example and look carefully at how we compute our estimates. Remember when we were doing the SVD thing, we had phi, which is U SV transpose, then we had the stuff in the middle, and then we had phi transpose. And this is now our analysis step, projecting onto phi. There's an adjustment step and a synthesis step. So notice what's happening here. After projecting T onto U transpose, we expand the results by the singular values in S, so that's what this is doing, and use the projections to form a linear combination of the columns of V. So whatever the result is, we'll use that to form a combination of V. But then, and this is where we start getting the adjustment, this is where the phi t phi minus 1 comes in. We immediately go back to the projection coefficient. So we've projected into V, we made a linear combination. Now we just use V transpose to like get back the elements of that combination. We undo this scaling that we did, and we kind of undo it twice. So that's why there's kind of a double scaling. And why? So we attenuate, we attenuate by the square of the singular values, and then form the linear combination of V again. And now why are we attenuating by the square of the singular values? Well, because we're going to do one more round of expansion on the way out. So we essentially do there's one round of expansion, then we cancel out twice, one more round of expansion. The net effect is no expansion. So, and what happens, we again go back to projection coefficients using VT, expand once more by S, and use the result to combine the columns of U and form our output. So we can view the role of this thing as undoing the double expansion that we apply to the input, changing it as little as we can. This makes sense because we're trying to make the output as similar as possible to the input, and any unnecessary expansion or contractions would take us away from the best solution. So that's kind of what it's about, right? So essentially what if you have any kind of overlaps, then this S matrix will start showing up and will perturb your result from being as close as possible to Y hat. So you need this adjustment in between to essentially cancel the effects of those overlaps, to make sure that, if you're kind of blowing things up in one direction and then blowing them up again, that in between you actually squish them back down. And any unnecessary, so we're trying to make the output as similar as possible to the input, and any unnecessary expansions or contractions would take us away from the best solution. Good, and then the final little piece, so that there's exactly one minimum. So we found one solution above. How can we be sure it's the only one? So from the geometric perspective, kind of convinces us that's the case, where there's only one minimum on that span. But let's just see it analytically. So we just go back to our equation for the gradient, which was this thing. And we differentiate with respect to W one more time to get the curvature of our function. So we differentiate this one more time, and we get this phi t phi, which using our SVD, it's VTS squared. I think maybe the V's, the order of transposes is reversed, but either way, it doesn't really matter. We can then compute the curvature along the directions given by the rows of VI, and so if we actually compute the curvatures, we see that there are all these positive numbers. So what this says is that if we rotate our coordinate axes to be the rows of V, then we'll find that our function has constant positive curvature along each of the coordinate directions. So if you go along each of those directions, the curvature is constantly positive as you go out all the way to infinity. And so in other words, what you have is a parabola in this direction, a parabola in this other direction, parabola in every direction. So what you have is overall one multivariate, multidimensional parabola. And it will have exactly one minimum, and which we can find in at least 3 different ways, which is what we did. So that's the end of the notes. Yeah, I hope you found that useful, just to go through it, try to do some linear algebra, try to combine it with some geometry, and try to get a real sense of what's happening. Yeah, I think it was kind of good practice. I hope you found it useful, and so this time please do leave some comments if you can, just to let me know whether you found this exercise useful, kind of going a little bit more in detail into the notes. If so, I'll do more of them. If not, I will do less. So yeah, so thanks for waiting for this content. Hope you learned something. Let me know if you didn't, and I hope to see you in the next video. Bye.